The use of complex numbers is vital in electrical engineering. Electrical engineers come in contact with various problems involving complex numbers in the analysis of AC circuits. Such alternating currents are useful in the building of electric generators, motors, and distribution systems, proving far more efficient than DC power sources. Here we are given an example of an engineering problem that requires an understanding of complex numbers. We are given the voltage and impedance in rectangular form and are asked to find the current in polar form. The formula for voltage is equal to current times impedance. Substituting the values from the question, we have 45 plus J10 divided by 3 plus J4 is equal to current. Transposing, we are left with this equation here. Now we must rationalize the denominator by multiplying the equation by 3 minus J4 divided by 3 minus J4. Expanding this, we have 175 minus J150 divided by 25. Simplified to give us a resulting current of 7 minus J6 amps, or A. Now that we have our current in rectangular form, we need to convert our result into polar form as the question requires us to. That is, voltage is equal to R angle theta. We know that R is equal to the square root of x squared plus y squared. Substituting our x and y values, which is 7 and minus 6, into the formula and simplifying, we have our value of the square root of 85 or 9.2. To find the angle, we use theta is equal to the inverse tan of y over x. Again, substituting for x and y, we have a resulting angle of minus 40.6 degrees. Therefore, in polar form, our current is equal to 9.2 angle minus 40.6 amps. This aspect of engineering that we have chosen can be applied in everyday life, which the average person can relate. The power factor of an AC electrical power system is defined as the ratio of real power flowing to the load to the apparent power in the circuit. Ranging between -1 and 1, a negative power factor occurs when the load is generating power. A load with a low power factor will draw more current than a load with a high power factor for the same amount of useful power transferred. This means that equipment with a higher power factor will cost a consumer more in electricity than a utility with a smaller power factor. We are able to find the power factor of a circuit using the problem we had solved earlier. Power factor is equal to cos theta of voltage minus theta of current. We found that our current for the circuit was equal to 9.2 angle minus 40.6 amps. We were given a voltage of V is equal to 45 plus J 10V. Converting this into polar form, we have a voltage of 46.1 angle 12.53 volts. Now substituting our angles for voltage and current in our power factor formula, we have a resulting power factor of 0.6.